Welcome to This Explainer. Today, we're tackling an absolute beast of a staff engineer whiteboard challenge, designing a real-time top K aggregation system for billion-scale traffic. If you've ever wondered how major platforms track trending videos, the most clicked products, or viral hashtags the exact second they blow up, well, you're in the right place.
So let's dive straight into the prompt. The challenge is asking us to build a system that receives billions of user actions and returns the top K most popular items at any given moment. We need to track these viral events exactly as they happen, handling massive, continuous inputs without the system completely buckling under the pressure. In the industry, we call this a classic streaming heavy hitter or top K aggregation problem.
Here's our game plan. First, we'll cover the top K prompt. Then we'll look at why databases fail, building the streaming pipeline, fast reads with Redis, scaling the bottleneck, and finally, trade-offs and wrap-up.
Okay, Section 1, the top K interview prompt and requirements. Let's map out the system physics and define what billion scale actually means for our architecture.
A billion actions a day sounds massive, right? It averages out to around 12,000 events per second, but we absolutely have to design for a peak of 100,000 events per second just to handle unexpected traffic spikes safely. On top of that, our non-functional requirements dictate a sub-50 millisecond read latency and 99.9% availability. Because we're optimizing for extreme speed and high availability at this scale, we're actually going to accept approximate top K correctness for our real-time views. We are prioritizing a lightning-fast user experience over absolute mathematical perfection.
The secret to absolutely crushing the initial stages of a senior or staff interview is precisely mapping those abstract domain problems to concrete data structures. For instance, we're going to use distributed counters for popularity, and we'll map our top K requirement directly to min heaps and Redis sorted sets to serve those incredibly fast queries. Getting this mapping right from the start is completely crucial.
Moving on to Section 2, why databases will fail. Now that we have our data structures, let's talk about the naive approach. If you try to do a raw SQL group by query over billions of rows every single time a user loads a web page, you will literally melt your database. The compute cost is simply astronomical. Because of that, we have to completely abandon the synchronous write path, where the client actually waits for the database to update. Instead, we have to use a decoupled asynchronous streaming pipeline. It's the only way to scale horizontally.
Section 3, building the streaming pipeline. The key takeaway here is how we separate volatile web traffic from the heavy-lifting aggregation layer. Our bifurcated workflow relies on a beautifully decoupled architecture. On the lightweight write path, our client API just receives an action, publishes that event to a durable Kafka queue, and instantly returns a status of accepted. That's it. The synchronous part ends right there. Kafka acts as our massive shock absorber, totally decoupling the ingestion layer from the heavy lifting happening asynchronously downstream, where our stream processors are actually consuming those events to update the rankings.
Inside stream processors like Flink or Spark, we're aggregating counts by item in time. But instead of trying to update one massive window per event, we use sliding 1-minute buckets. We basically tally up the events per minute and then merge the last 60 buckets for a rolling 1-hour view. It's incredibly flexible. By just adjusting how we merge these buckets, we can effortlessly support windows for the last 5 minutes, 1 hour, 24 hours, or even all-time rankings, all without redesigning the core system.
Section 4, sub-50 millisecond reads with Redis. Once we have those aggregated buckets calculated, we need a way to serve them to users instantly.
And this brings us to the golden rule of our entire design. The read path never scans raw events. Never. Instead, our stream processors are continuously updating materialized views in Redis. So, when a user requests the top trending videos, the API executes a blazing fast order of n read using a single command, like zrevrang, directly on our pre-computed Redis sorted sets. We do the heavy math once, and we read it millions of times.
Section 5, scaling the right bottleneck. We've got a decoupled pipeline and lightning-fast reads, but any good interviewer is going to push you right here. Think about what happens at peak scale. Say the World Cup final is happening, and we're trying to write 100,000 updates a second to just one single global Redis key representing our top K list. That creates a massive hotkey bottleneck. That single Redis node's CPU will completely max out, and it will choke our entire streaming pipeline. We need a way around this.
The elegant solution is something called a local plus global merge. Instead of writing every single update to one global list, we compute a local top K inside each aggregator node partition first. Let's say we have 100 aggregator nodes processing data. Each node finds its own local top 100 items. Then they periodically flush just those tiny local lists to a global top K merger. Let me tell you, merging 10,000 pre-aggregated candidates in memory is infinitely faster than trying to sort a billion raw events. This pattern right here is the absolute secret to surviving billion-scale traffic.
Section 6. Resiliency, Trade-offs, and Wrap-Up. Now, a staff-level design isn't just about the happy path when everything runs perfectly. We have to address things going wrong.
Failures are guaranteed, right? So we plan for them. If a consumer node crashes, we simply replay from our committed Kafka offsets. Because Kafka is durable, zero data is lost. If our Redis rankings somehow get wiped out, we just rebuild those sorted sets directly from our persistent storage. And because we can confidently replay data, we prevent double counting through strict downstream deduplication.
Speaking of duplication, to handle idempotency, making sure an action is only counted exactly once, we use at least once processing paired with Redis SNX for incredibly fast deduplication. But what about a user voting from a phone that loses cell service, causing their event to arrive way late? We handle this by setting a 10-minute watermark. If the event arrives within 10 minutes, we process it normally. If it arrives outside that window, it gets pushed to a separate batch reconciliation path, keeping our real-time stream perfectly clear.
Looking broadly at our architectural trade-offs, we completely rejected the database-only approach because it's just way too slow. We rejected a direct-to-Redis approach because of that fatal hotkey write bottleneck we talked about. We explicitly chose stream processing with a local-to-global merge because it's highly scalable, the data is totally replayable, and it gracefully handles massive throughput via that decoupled ingestion layer.
Synthesizing all of this together, we've built a seriously robust architecture. We leverage durable Kafka ingestion to isolate giant traffic spikes, Flink for powerful windowed aggregation, and Redis materialized views to serve our users instantly. Together, this creates pragmatic, billion-scale consistency that an interviewer would absolutely love to see on a whiteboard.
But I want to leave you with this thought as we wrap up. We built a pipeline focused on exact event processing and precise deduplication. But what if you could sacrifice just 1% accuracy in exchange for using 10 times less memory? You could do this by implementing a probabilistic data structure like a count-min sketch. How would that fundamentally change your design? Would you even still need the same massive Redis cluster? It's a fascinating trade-off to consider as you design your own systems. Thanks for joining me on this explainer, and keep building great things.